Hey, good morning, guys. So today, our lesson will be on atomic radius. If I ask you, what's the word radius? Most of you are going to say, okay, yeah, you have a circle, and from the center to the most outer part of the circle, that's known as the radius. And that's what my math teacher told me a long time ago. Well, yeah, of course. Of course, that's what it is. But what does it mean when people say atomic radius? What are they indicating? Well, like the radius of a circle can be used to determine the size of the circle. Okay, the atomic radius is basically looking at the size of the atom. How big or actually how small are these atoms compared to one another? Looking at the periodic table of elements. So, do you think that the atom actually get bigger and bigger and bigger as you have more and more protons? Because so far, okay, we've been looking at periodic trends, and we know the periodic table is organized in a way where you have increasing number of protons, most likely the increasing of atomic masses. Well, as atom gets more protons and becomes heavier and heavier, are they getting bigger and bigger and bigger? The answer is obviously no. Okay, it's not. The atoms at times may be getting smaller, even though there are more protons being added. Like when? Well, here's the trend, and then I'm going to explain exactly why later. Okay, so let's draw the trend. The trend here is this. As you move across the periodic table from left to right, the atomic radius, the size of these atoms, are actually decreasing. They're actually getting smaller, believe it or not. Okay, so if you were to compare hydrogen versus helium, which one is bigger? Hydrogen is actually bigger. You may be thinking, but helium has more mass, more protons. Shouldn't it be bigger? Well, this is the part where we're going to have to look at the Bohr model of the atom to determine, okay, along with some other attributes. So let's take a look at the other trend then. Going down the group. Okay, as you go down the group, it's not surprising that it is going to be increasing. It's going to get bigger and bigger and bigger as you move down the group. So if you were to compare, let's say, lithium versus sodium, sodium is bigger. You can easily tell for that one. Okay, because when you were drawing these Bohr models, these guys have an extra shell compared to these guys, so it's not surprising that these guys are bigger, isn't it? But why this is decreasing across the periodic table is what's interesting, and there are actually three contributions to why the atomic radius has a certain trend like this. So let's go over these three factors, okay, that result in the trends of atomic radius being decreasing across the periodic table and increasing going down the group. So, number one. The first factor is obviously an obvious one, energy level. Okay? Would you abbreviate it by the letter N? The higher the energy level, okay, or the more energy levels there are for an atom, the bigger they are. And for atomic radius, Bohr model of the atom is actually a very good, useful model to illustrate this. All right? So if you think about it, you have lithium, okay? Lithium will have 2 electrons on its first shell and 1 electron on its second shell. Right? But if you look at his friend, sodium, that is really just right underneath him, Sodium will have more shells, an extra shell. 2 on the first shell, 8 on the second, and 1 more on the third. Really not surprising at all, okay, in terms of the first factor, that more energy levels, bigger. Okay, what about going across the period? What about going across this way? What can you say about the energy level as you go across the group? Not surprisingly, the energy level stays the same, right? Right? If you were to, let me get rid of the sodium. Let's say you were to draw beryllium, which is really next to lithium. Beryllium will, like lithium, will have 2 electrons on the first shell and 2 electrons on the second shell. Let's put them like this. It's not entirely correct, but then let's put them like this. The number of shells, the number of energy levels stays the same. But why is it decreasing is the question. And this, of course, will bring me to my second factor that contributes to atomic size. The second factor is nuclear charge. Okay, nuclear charge, of course, based on number of protons. Protons, we all know, are positively charged. Electrons, like these ones, or these ones, are negatively charged. These are something that we already know. Okay, let's talk about stuff that we don't know. So when you look at lithium, for example, lithium will have a nuclear charge of 3 protons. Okay, beryllium has a nuclear charge of 4 protons. 4 protons. So if I ask you a question, a very simple question, which atom has a stronger nuclear charge? I hope your answer is beryllium, because the number of protons here is just more than the number of protons in lithium. So beryllium's nucleus has more positively charged proton, which have the ability to attract these electrons. Basically, this is a stronger, let's say, magnet than this, pulling these electrons inwards more. Now, you may be thinking, but there's more electron those, but that doesn't matter. It's not like you have an extra shell or anything, right? So if you think about nuclear charge, as you move across the period, the nuclear charge is going to get bigger and bigger. Let me just blow this up right here. It's going to get bigger and bigger and bigger and bigger and bigger and bigger. Which means, think about magnets as an example, you're getting a stronger and stronger and stronger and stronger positively charged center, sucking the electrons more inwards and more inwards. That's why, as you move across the period, the atom is actually getting smaller because of that. Okay? Because of the nuclear charge just getting stronger and stronger and stronger. Okay? So if you think about, neon as an example, looking at period 2, neon will have a nuclear charge of 10. Now that's a big deal, right? That's strong compared to 3. Even with the case that there's, more electron, but it really doesn't matter in this case. Okay? These electrons will actually be attracted more inwards towards the nucleus because the nucleus is strong. Okay. Now, what about going to the next element? What if you have 11 protons? Like right here in sodium. Sodium has 11 protons. Even that, is sodium going to be smaller than neon? Of course not. We mentioned this before. Okay? If you look at sodium as an example, sodium is going to be big. Why? Because of that extra energy level that it has. Extra energy level is a big deal. But if the energy level stays the same, like these three, all three of these has 2 energy levels, well, then energy level doesn't play a role here, but the nuclear charge does. Because when nuclear charge increases, it's going to get smaller and smaller and smaller. Even though, in terms of my drawing, this is actually bigger than that. But really, in reality, this is actually much smaller. Neon is actually much smaller than lithium. By quite a bit, too. But once you start adding these extra layers, okay, it's a different ball game now. I hope you guys are okay with that. Okay, so we've looked at the first factor, which is, of course, an extra energy level. We looked at the second factor, which is, of course, based on nuclear charges. And let's take a look at the third factor. Let me erase all of this. The third factor is really another way of interpreting the first factor, and that is shielding. Okay. What do you mean by shielding? Well, we all know what a shield is. It's the block, right? So let's take a look at sodium and potassium as an example. So we have sodium right here. 2 electrons on the first shell, 8 electrons on the second shell, and 1 electrons on the third shell. Okay? Potassium, well, we can easily determine the fact that potassium is going to be quite a lot bigger because potassium will have an extra layer of energy level. This is potassium. Okay, 4 energy levels in a total of course 19 electrons with an extra shield, an extra energy level of 4. Well, we know because of the first reason that this guy's bigger because of the extra shell, right? But that's not the only, of course, reason. Another reason, of course, is based on shielding. Okay, the atomic radius is determined from the nucleus to the outermost, the distance of the outermost electron. The valence electron, to be exact. So you're looking at this distance right here. Okay? Remember, in the second reasoning, there is some sort of attractive force between the nucleus and its electron. What can you say about the attractive force between the nucleus and this electron? Is it going to be greater versus this and this? Okay. Now, you can easily tell that the attractive force is actually weaker from here to here versus here to here. Why? Because of these guys. You see these electrons right here? They're acting as a shield. They're blocking the attractive effect between the protons and the electrons right there. These protons want to attract these electrons, no doubt. That's what they do. But these electrons are there, blocking the effect. If there's some sort of attractive force between here and here, these guys just kind of ruined it. That is shielding. If you look carefully, of course, there is 3 layers of shielding for potassium, and really only 2 layers of shielding in sodium. So you can see that the shielding effect between the sodium's nucleus towards its valence electron is less than the shielding effect of potassium's nucleus towards its valence electron. 3 layers of shielding versus 2 layers of shielding. This is less shielding, so therefore the attractive force is stronger here than here. Okay, stronger attractive force, smaller the atom, because the most likelihood of this electron getting sucked in is more than this getting sucked in. So what that means is this, though, which means if you were, and we're going to see this very soon, if you were to take this electron away and turn this into an ion, it's actually easier to take this away than to take this away. It's almost like you're playing tug of war with the nucleus, man. Because the attractive force is much stronger here because there's less shielding. If you want to take this away, you better supply yourself with much more energy than this. Because there's more shielding here. This is less attracted to the nucleus. So therefore, if you want to remove this electron, which you want to, oh yeah, potassium will love you to remove this electron. This is going to be easy to remove. I can tell you this right now. We're going to be talking about reactivity at the end of this. Reactivity. How reactive these things are compared to one another. Potassium is more reactive than sodium. How do you know? Well, for a metal loves to have their electrons removed because metal wants to be cation. The easier it is to remove an electron, the more reactive this metal is. Let me say that again. The easier it is to remove an electron from a metal, the more reactive it is. So if I were to ask you a question, which I will ask you on in your course pack, which element do you think is the biggest on the periodic table? Because that element most likely is the most reactive as a metal. As a metal. Let's not talk about non-metal because there's a different contributing factor for non-metal, but as a metal, the biggest metal, the most reactive it is. In fact, this metal, okay, doesn't even exist long enough for you to actually see the effect. Okay, so radioactive, so unstable, that doesn't exist long. I wonder who he is. Okay, let me know on the comment section below. Anyway, that's atomic radius. So remember, for atomic radius, it decreases as you move along due to nuclear charge and increases going down the group due to the amount of shielding and the extra layer of energy level. Anyway, let's call it for the day. And tomorrow, let's look at ionization energy. Bye now.